Hello, and welcome back to week 3 of financial mathematics. So far, we have started chapter 1, interest rate, in 2 weeks. Since this is likely the first course many of you take in actuarial science, so I think it may be a good idea for me to do a quick review for you on chapter 1 and in the future, I would really like you to do this kind of review on your own. Basically, all you need to do is to get a piece of blank paper and start writing down what you have studied for that specific chapter. And once you practice this, in the end, you should be able to write down most of the important topics you have learned from any particular chapter and add on some of your own understandings or interpretations of important theorems or concepts. Okay. So here is my example. This is how I would review chapter 1. Again, you may have different version. Again, this is me doing one example only. So we begin with interest. So what is interest? The reason we have interest is because money has time value. So the essential idea in this is money has time value. Okay, so time value of money. Because money has time value, so your account at this time is not the same as the account value in the future, right? So if you draw a timeline, let's call this present. Let's call this future. So the amount in your account is likely to be different, right? When time moves from present to future, okay? And that's particularly the case when you get a loan. So let's say you borrow some money from a bank. What you borrow right now is the present value of the loan, right? And when you pay back the loan to the bank at some future time, okay, the size or the amount you need to pay back will be higher than the original amount you borrow, right? So in that example, the interest is nothing but the difference between the future value of the loan and the present value of the loan. Okay, so let's say we have a simple example. Let's say you borrow $1,000 from a bank. In 1 year, you need to pay back $1,100. So in this example, in 1 year, you pay back, okay, so I can remove the quotation mark. The original amount you borrowed is $1,000, right? And the difference, $100, is the interest you paid to the bank for getting money from them, right? So that is the cost, right? And in this particular example, we are talking about amount. Okay, amount is the interest, but it's often inconvenient, right? So here you borrow $1,000, and the amount you pay extra is 100. So here the actual amount is 100. Let's say there's another loan. The interest that you pay is, let's say, 500. How do you compare those two loans if you only know the interest, right? In reality, there's no way for you to compare the amount, right? Of course, in this case, 100 is less than 500. So if you are a borrower, the cost is less, right? In 100, but a lot more in 500. But you don't know, right? That may not be the case. What you look at is the actual amount. What if you borrow, let's say, 8,000, and you only need to pay additional 500 for this loan? Actually, you are getting a better deal in the second case, right? So if we label this is the first loan, this is the second loan. If you only look at the amount, the interest you're going to pay in the first loan is smaller than obviously the second one, right? But if you average to each dollar, you are paying less in the second loan. That is very obvious, right? So for that reason, it actually makes more sense to consider the percentage of cost, which is interest rate. Okay, when you calculate interest rate, it's somehow normalized, right? So in the first loan, it will be the amount you pay divided by the original size of the loan. So it's about 10%. In the second case, the amount is 500 and the original size is 8,000. You can do the calculation, right? It's obviously less than 10%. So you are getting a better deal from the second loan. Okay, that motivates us to study the interest rate rather than interest itself in pretty much all applications. Okay, so interest rate in this example, it tells you the cost of a loan. Of course, in the general case, it could be the benefit of a deposit. Right? Let's say you deposit money into a bank. So what the interest rate in that case gives you the benefit, right? So it's how your account value grows. In that case, the higher the interest, the better the case to you. Okay. So to study interest rate, we have introduced 3 forms. The first one is simple interest. The second one is let me get a different color for the title. Okay, so the first one we study is simple interest. The second one we study is compound interest. The last one we have studied in chapter 1 is continuous interest. Okay, by the way, we often call this force of interest. So that is the headline for the 3 different forms. We define them according to accumulated value. And it's more convenient to consider the unitized. So which means the account value at time 0 is 1. So we call this accumulated value factor, AVF. So by definition, so let's put a bracket. If you have simple interest with I being the annual percentage, so when we quote interest rate is always per annum in chapter 1. Okay. What is the AVF in compound interest? We take 1 plus I to the t's, right? So we raise the power to t. In the continuous interest rate is exponential of delta t. So in convention, we use delta instead of I in the force of interest. How do we equate them between I and delta? So you simply take t to be 1, right? Let's do a little calculation down here. I put a little box. So in order to equate compound to continuous, we take t to be 1, then we have 1 plus I equals E of delta t, right? From there, we know delta is nothing but log 1 plus I. So if you know the force of interest being delta, we can take the exponential and minus 1 to get the compound interest rate I. And if you know I, you can use 1 plus I and then take logarithm to get delta, right? So that's the relation between I and delta. What is the most important feature under each of those interest rate forms? When we have simple interest, the amount that grows over any year is fixed. It's I. So the amount here, delta means the amount of change. the amount of the changes is a constant and is equal to I. But if we consider compound interest, it is rather the percentage of changes is a constant and it is I. Okay, so this is percent of change. So the percentage of the changes is a constant I. In this case, it's the same, but the percentage is no longer I. It will be E of delta minus 1. Again, that is not difficult to understand. It directly comes from this box, right? Because I is E of delta minus 1. So in the last two cases, the percentage change is a constant. In the first simple case, it's the amount of change is a constant. If we draw a quick graph, okay, so the horizontal axis is time, the vertical axis is accumulated value factor. So at time 0, so assume you have $1, okay, and your simple interest grows like this. This is simple. It's a linear function. It grows linearly at the same speed. But if you are at compound or continuous, you will grow like this, right? The second, compound, compound and the continuous, they are very similar, right? Continuous is the limit of compound, and here the shape of the graph, of the last two forms is rather similar. So I only use one dotted line to denote them. We know when do you cross 0 and 1, right? At 0, your value is 1 for all of them. At 1, it is 1 plus I. Right. So for 1 year, it really doesn't matter, right? So if you consider a 1 year loan, all three interest rate forms will give you the same result, right? It's the same. Only when the number of years is less than 1 or greater than 1, you will have something different, right? So if you have longer term, the compound interest grows much, much faster than the simple interest, okay? So that is the basic review of the three interest rate forms we have studied. There are a few additional remarks. So when we study simple interest, by the way, we often apply simple interest for very short period. So if you, let's say, a good example is the treasury bills issued by the U.S. government. It's usually 3 months, okay, and of course you can get shorter, but 3 months is the common one. It's the term of the loan or the term of the bond is 3 months, which is less than 1 year. And in this case, let's say your interest is quoted as I per annum, and let's say you only have 30 days. Of course, in that case, you can think it's 90 days. And how do you convert to calculate? Because according to this, is 1 plus ti. So in this case, the question is, how do we compute t? Right? We only have 30 days. So we need to convert the amount of time into a fraction, right? Because we do not have 1 year. We only have 30 days. There are different rules to convert. That is something we covered called the day convention rules. Right. So let's say we use actual and 330. So in one example, let's say we use actual over 330, and my interest rate per year is 5%. I assume between two dates, they are 30 dates. So in order to calculate this, my ADF at t will be 1 plus T is calculated as the actual number of days. In this example, I call it 30, divided by the denominator is 360. And I know my annual interest rate is 5%. So this is basically what day convention rules do is to tell you how you can convert number of days into number of years. Okay, of course, it's going to be a fraction of years. I think I may test you one question on exam one, only one, no more than one. Okay, in the next, I'm going to talk about something very, very important. That is about three important notations, I, we, and D. Okay, let's begin with the most understandable case. Let's consider 1 year loan. So in all of those examples, I consider 1 year loan of $1. Okay, so that's the unit size. Okay, and interest rate. Interest rate is I% per annual. So it's annual interest rate. Here is time 0. Here is time 1. Okay, I borrow $1 at time 0. According to this setup, how much do I need to pay back at time 1 in 1 year? Right? I don't need to specify whether it's simple interest or compound interest because when t is 1, they are the same. Right? So if I borrow $1 at time 0, I'm supposed to pay back the lender 1 plus I in 1 year. Okay, so here I can break this amount into two parts. Okay, this is the original amount I borrowed. Usually we call this principal. The second component is I. This is interest. Right? Because this is a unit loan, so the interest is the same as interest rate. Okay, here what I want to emphasize is that this interest is, let me emphasize, is paid at time 1. So I pay back $1 principal plus I dollars interest at time 1. So that is the maturity time of this loan. Okay, you may wonder, but before we do that, is how do we interpret this result? What we can interpret is that using the concept of time value of money, this is the same account. The account at time 0 is worth 1. The account at time 1 is worth 1 plus I. How do I go from $1 at time 0 to 1 plus I dollars at time 1? The way I go from 1 to 1 plus I is by times by this factor, right? Which is 1 year AVF. Okay. What if I want to look at this problem from the opposite angle, the reverse direction? How do I convert 1 plus I dollars at time 1 to something at time 0? Right? I know from 0 to 1, from present to future, I times by the AVF. In this case, it's just the 1 plus I. Okay. If I want to go backwards, I need to times by discount factor. And obviously, $1 at time 0 is equivalent to 1 plus I at time 1. Then, according to this should be exactly $1 at 0. So I know my V will be 1 divided by 1 plus I. Right? So that's how I go from future to present. Right? So basically, what V does, this small v does, is to help you quickly convert some money in the future to the present. So let me briefly summarize the difference. So AVF what it does is from present to future. So in my example, it's $1 at time 0 to 1 plus I at time 1. What present value does, well, let's put PVF, is exactly the opposite side, is to convert some value in the future time to the amount in the present time. Of course, future and present are relative concepts, right? In this example, 0 is present, 1 is future, right? But if I have second year, then 1 is present to relatively to the year 2, right? Okay, so that so far I have explained I and V. Somehow the more complicated part is D. In the first scenario, I pay back both principal and interest at time 1. Okay, in the second scenario, I switch the conditions. I don't want the borrower to pay the interest at time 1. I want interest to be paid at time 0. Okay, so again, we know, let's draw the timeline. So this is I dollar, right? This is interest. If interest is to be paid at time 1, the amount will be I. Now I want interest to be paid at time 0. How much would that be? It will be, well, simply times by the discount factor, right? That's how we go from future to the present. So the amount is I times by the discount factor V, okay? This is how I write V, it may be slightly different from how you write V. So this is V, Victor. So if we name this, we put a name, we call this D. So how do we interpret D? D is nothing but the amount of interest, okay, paid at time 0 in order to get a loan of $1 for 1 year, right? So if you want to borrow $1 for 1 year, the cost to you at time 0. So the most important thing is this is the cost at time 0, and that cost is D, the discount. Okay. If I repeat, what is I? Is the amount of interest paid at time 1 in order to borrow $1 for 1 year. So the essential difference between D and I is time. If you want to pay your interest at time 1, you pay I. If you pay the interest at time 0, you pay D. Obviously, D is smaller than I, right? And the connection is D equals I times the discount factor V. So that's everything. So from here we see I is the future value of D. Of course, here we talk about 1 year. D is the present value of I. So that is the connection. So with that in mind, now we want to borrow $1. We still want to borrow $1, right? And when you get the loan, you actually need to pay the interest. So effectively, in this example, still the loan example, so what you actually borrow is 1 minus D, right? You want to borrow D, but you need to pay the, you want to borrow $1 loan. And at the same time, you need to pay D dollars of interest. So if we break this, so $1 is what you borrow. So it's the loan side, okay, principal. D is the interest. It's like you prepay your interest at time 0. At time 1, you pay back $1. You only pay the principal because you have already paid the interest at time 0. So sometimes we call this the effective loan, because effectively you borrow 1 minus D and you pay 1. So in this effective setup, we know 1 minus D at time 0 will grow to 1 at time 1. So right. So now let me erase this. Let me sum up everything. If I start, so it's always from time 0 to time 1, okay? So that is something I need to mention. It's always between time 0 and time 1. If I start with $1, I will get 1 plus I, right? And if I start with D dollars, I will end up with I. If I start with 1 minus D, I will end up with 1. Okay, that's just the if you use here 1 minus D, you get 1 minus D, right? If 1 plus I minus I is 1. So it's simply, of course, it is also two-way traffic. So that is the entire secrets of this chapter, right? All you need to do is to draw a timeline, right? If you start with $1, you end up with 1 plus I dollars in 1 year, right? So if you have I dollars in 1 year, the current equivalent value of that size is D, right? And if you borrow 1 minus D at time 0, you pay back $1 in 1 year. So that's everything I need to say about the relation between or among I, V, and D. Okay, and hopefully that clarifies everything. In the end, I want to add 2 more remarks. Okay, so first, the force of interest does not have to be a constant. It can be a function. So the amount can change as time changes. In that case, my AVFT will be an integral, so exponential of an integral. So from there, you need to do some calculus. So please review calculus rules, basically antiderivatives, for at least for exponential function, for log function, for power function, right? Those elementary functions. There's no need to study trig functions. I do not ask you trig functions here. It's usually power function, log function, exponential function. Okay, and I need to emphasize a little bit more what I did slightly inappropriately, excuse me, in the first chapter. I studied the concept of M's compounding earlier on, and M's discount, right, which shouldn't appear in chapter 1, okay? So this is the topic of chapter 4. But I think some of you probably can't understand at this moment. If don't, so if you can't understand at this moment, it's fine for now. So you can skip this part, and we will revisit M's compounding when we study chapter 4. Okay, so those will not be in exam 1. So in the exam 1, we will not test M's compounding. So whenever we talk about compounding or compound interest rate, it means we compound once a year. Okay, for that reason, when you see effective interest rate, that is the same to say you have compound interest rate per year. Okay, so again, that is the default setup. Since we are not supposed to study M's compounding, so there's no confusion at all. Whenever you talk about the effective interest rate, we can use the compound interest. Okay, so that's the end of my review.